All right, well, let's go ahead and pick up where we left off. We're going to do a couple more algebraic things with vector value functions, just so that we understand them. We've obviously related them to parametric equations, so let's go ahead and do one that actually explicitly does that. Let's say, and this is number 14 in your book, probably a good idea to follow along in your book so that you can see the instructions. Let's say that we're given negative 3, 4, and 2, 8. Okay? Now those are 2 points on the Cartesian plane. Okay? And we need to know, let's say we want the vector value function and the parametric equation, so we want both, that passes through those 2 points. Okay? Now here's the thing. You would think that vectors, well, vectors you can just pick up and move anywhere and they're all the same, so why does it really matter, these two right here? Can it be any two? Well, that would be true if we were dealing with numerical vectors, but you got to remember that the numbers that the vector value function spits out are the terminal side, okay? And if the initial side of all vectors for a vector value function, if the initial point is always the origin, then it matters exactly where in the Cartesian plane the terminal side is, okay? So it actually, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2. So what we have is we have this point right here and this point right here. Okay, and so we want the line that goes through there. Now finding the parametric equations of that ought to be easy enough. We've done that before, okay? You know that to go from here to there, you move up 5 in x, so your change in x is 5, whenever your change in y is 4. Okay? And then for parametrics, all you need to do is pick one or the other, and let's go ahead and pick this one. So we know that x of t and y of t, well, I know that it's going to be, let's just pick this one as the point, negative 3 plus 5t and 4 plus 4t. And that would be a very good way of representing the parametric equation pair for that particular line. Now remember that the difference between parametrics and vector value functions is that those points are not points in and of themselves. They are the points which represent the terminal side of a bunch of vectors, and as points on that line move, you can sort of see the vector sweeping through space and sort of moving to the right and getting longer as it goes, okay? But it still winds up being the same representation in terms of x and y displacement. It's still 3 plus 5t and 4 plus 4t, okay? And you just got to remember that that acts much like the slope. So actually you could go ahead and actually write the Cartesian as well, right? You know that change in y over change in x is 4/5, and you know that any one of these points will do, so y minus y1 m times x minus x1, and there's your Cartesian as well if you're asked for it, okay? Well, let's move on to the next problem, where indeed you are asked for vector, parametric, and Cartesian. This is number 17 in 10.4. But they don't give you the same information. Instead, they give you just a point, negative 4, 5, and then they tell you that it needs to be parallel to that vector. Well, if it's parallel to that vector, then that's basically a nice, nifty way of saying, there's my delta x, and there's my delta y. Okay, so this actually is even easier because I didn't have to find my delta x and my delta y. And so we have x of t is equal to negative 4 minus 2t, and y of t is equal to 5 plus 6t. My r of t is going to be the same the same expressions just put into component form of a vector value function, and then y minus y1 is equal to mx minus x1. Well, what's my slope? It's delta y over delta x. 6 over negative 2, that's negative 3, and I'm done. Okay. Well, that kind of brings us to the close of what we're doing here in terms of the algebra of these vector value functions. Let's move on to actually doing a little bit of calculus with them. Now, here is how they're different than parametrics. Usually when we're dealing with parametrics and we're looking for the derivative, we're actually looking for dy dx. That is not what we're doing here, and we're still in 10.4, and this is number 25. Okay, let's say that we are asked for the domain and the derivative of this. Well, let's not stop at the domain. Let's actually see what intervals are implied for t, x, and y, okay? Well, I know that there's no limitations here. I know that the outputs right here are limited, right? They're not going to go below negative 4. But there's nothing that actually limits the input, right? Here, however, I do have impossible inputs because I know t minus 4 has to be greater than or equal to 0. So t is greater than or equal to 4. So I know that with respect to t, 4 to infinity is my interval. Well, then I have to go back and see what kind of values that actually gives me for this. Now, I know what kind of value it gives me for this. I've seen this before. This goes 0 to infinity, right? So my y, or my horizontal, my vertical component, this goes 0 to infinity. But my x right here, if I plug in 4, that gives me 16 minus 4, or 12, but then it just keeps going on up from there. So in terms of x, this is actually 12 to infinity. So the implied restriction here on my vertical component actually winds up limiting where my x component can actually go, because they have to work in tandem, right? Well, that's easy enough. Let's go ahead and move on to actually taking the derivative. I am not worried about eventually finding dy dx. I simply want to find dy dt and dx dt. But I want to do it in this component form, okay? And therefore, t squared minus 4 just becomes 2t, and root t minus 4 becomes, by the power rule, 1/2 t minus 4 to the negative 1/2. And you're thinking to yourself, is it really that easy? Oh yes, it's really that easy. Okay, well, let's go ahead and move on to another example. We'll go ahead and skip the domain aspect because I think we got that down. Basically, all of the intervals basically have implications for each other, so you just need to find where t is limited and see how it impacts x and y, or the horizontal and vertical in your component. Now, this one's going to be a little bit nasty, and what would be the fun if it wasn't? Okay, now, I see the fact that that's going to require the quotient rule on both of them, okay? So let's go ahead and do that. I know that that's going to mean the bottom, okay, times the derivative of the top minus the top times the derivative of the bottom. And again, I'm using those brackets to show where I've taken a derivative and where I just have an expression that's been carried over. Okay? And of course, we do the same thing here. We say the bottom times the derivative of the top minus the derivative of the top times the derivative of the bottom times the top, which is just t. All of that over t squared minus 1 squared. Now that's nasty, but it does clean up just a little bit. Let's go ahead and do a little bit of distribution. It's 2t squared plus 2t minus t squared, all of that over t plus 1 squared. That's t squared minus 1 minus 2t squared, all of that over t squared minus 1 squared. And then I just have to do a little combining of like terms in that numerator of both of those. And so I have t squared plus 2t over t plus 1 squared, and negative t squared minus 1 over t squared minus 1 squared. And that would be the derivative, okay? Because because you're worried about the components, you're just interested in how each component is changing with respect to t, okay? Now, let's go ahead and let's move on to number 27, which is a little more difficult. It is actually asking for a tangent vector, and not just any tangent vector. That would be hard enough. But let's actually find the tangent vector first, okay? Okay, let's say we're given r of t, and r of t is 2t, 3t squared, and we're looking for the tangent vector at t is equal to 1. Now, let's go ahead and take the derivative, and that's going to wind up being 2, 6t. Now, I happen to know that I need to evaluate this. Well, I would suspect, and in suspecting you would be right. That is the tangent vector right there, 2, 6, okay? Now, if I wanted the unit tangent vector, remember when we're finding a unit vector, we're finding a vector in the same direction as the original, okay? Same direction as this. So basically, the ratio between the horizontal and vertical displacement have to be the same. But I need it to only be 1 unit long, which means I need to figure out how long this is, and I need to divide this particular vector by its own magnitude, okay? So we'll call the unit tangent vector capital T. And so what we need is r prime of 1 over the magnitude of r prime of 1. And this is just Pythagorean, okay? So really what we have here is if this squared is 4 and this squared is 36, the sum of which is 40, we have 1 over root 40 to 6. And if that's 1 over root 40, that's 1 over 2 root 10, okay? 1 over 2 root 10 to 6, which means when I multiply it through, I'm going to get 1 over root 10, 3 over root 10. That is the unit tangent vector of this particular vector value function at that point right there, okay? I think you're going to understand a little bit more about what this is all about the moment that I actually do this next problem, okay? So let's say I'm given, and this is number 35, r of t is equal to e to the 2ti plus e to the tj, and I want the tangent vector, not the unit tangent vector, but just the tangent vector at t is equal to 0. Well, like I said before, I really like it in component form more than unit vector form, so let's go ahead and put it in component form. That's supposed to be a comma. It's a really bad one, but bear with me. So I need to go ahead and find r prime of t, and that basically, when you're, easy enough when you're taking the derivative of exponentials, especially with the base e. And then I need to find the derivative vector evaluated at t is equal to 0. Sorry about that. And so that winds up being 2 e to the 0, which basically gives us 2, 1. Well, the instructions here in this particular subset of problems says sketch the plane curve with the given vector equation. Find r prime of t. Well, we haven't sketched the curve yet, so let's go ahead and do that. Now, this should be easy enough, okay? If you turn into parametrics and eliminate the parameter, it actually winds up being root x where x is greater than 0, okay? And you have to stipulate that x is greater than 0 because here x can be 0. Here it can't, okay? So you have to remember that the original components, the form of those, will sometimes impact the certain limitations, and those sort of implied domain issues need to come over and be stated explicitly in the new problem. Okay, so let's go ahead and do e to the t. Okay, so we see that that's e to the 2t and e to the t. Let's go ahead and graph it. Okay, now remember, that started off really, really slowly because remember that e to the t and e to the 2t start out really, really flat and then accelerate very, very quickly as they pass into positive integer input values, okay, or just positive input values, not integer. All right. But you have to remember that even though we can't see it on the calculator face, I would really like to go ahead and put a circle there reminding us that that point actually does not exist on the graph. And what we have here is that. Okay, well, here's the thing. At t is equal to 0, the actual original function, vector value function, is at t is equal to 1. I mean 1, 1, the order pair. So this is r of 0. But what happens is when we do it this way, it winds up being that right there, however, is showing basically the velocity of that vector value function at time t is equal to 0. That 2, 1 has to be placed where r of 0 actually has its terminal point, because I mean it's showing the velocity at that point, right? So when t is equal to 0, r of 0 winds up being e to the 0, e to the 0, or 1, 1. So at 1, 1, we have a velocity of 2, 1. Okay? That kind of brings us to a close on this particular video. That's a nice place to stop, because the rest of the problems deal with integration rather than differentiation. So this has been sort of the differential calculus of vector value functions. In the next, and I think the final video for vectors, we'll get into a little bit of integral calculus for vector value functions, and then from there we'll move on into the realm of polar, which I think is far more exciting than either parametric or vector value functions. Unfortunately, the writers of the AP exam don't agree with me, so it doesn't show up quite as often there. But worth going over because it shows up often enough, and you're certainly going to be tested on it in your class here on Wednesday. So, as always, any questions, please do email me.